with spacecraft, it has to be with a dish antenna. And a dish antenna has directional sight, meaning you have to face it to talk to it. And as you know, the Earth is not flat. We figured out a few years ago. And space is not flat. And so if you can only talk to things you're facing, you're clearly not facing all of space at the same time. And the Earth is rotating, kind of giving us this 360-degree view of space. So the good thing is, at some point we'll be facing, where our spacecraft are. But what if that's not at the time that we need to communicate? And when we were thinking about sending people to the moon, that was going to be a big issue. If we had to time it perfectly so that Neil Armstrong was landing on the moon when the United States was facing the moon. Right? So here at JPL, we kind of took the challenge under our wing, and we said, okay, we'll make a network that can see anything in space, anytime, anywhere. And what we came up with was the Deep Space Network. And the DSN is actually comprised of 3 different chunks of locations. So we have one here in California, in a place called Goldstone, which is in the Mojave Desert. We have another one in Madrid, Spain. And we have another set in Canberra, Australia. So those are our 3 locations of antennas. And if you look at a globe, you'll notice each of those 3 places are about equally spread apart, approximately along the equator. And the way it works is, as one set of antennas rotates out of sight from our spacecraft, the next one has already rotated into sight. So we literally have full 360-degree coverage of the sky, 24 hours a day, 365 days a year. And that makes it unique to the planet. We take wireless communication for granted these days. It's like, oh, it must be pretty easy to talk to your spacecraft, with the type of communication capabilities that we have now. But believe it or not, this is the only thing on the planet that can talk to things in deep space with that full coverage. So because of that, JPL is not only tracking all of our own 22 active missions right now, we're tracking missions for other NASA centers, and we're tracking missions for other countries around the world. So it's a great asset for JPL. Now in 1964, when we built this room, we intended on every mission being controlled from this room. And when you only have 2 missions at a time, that's pretty easy to do. It takes on average 5 to 10 people at a time to control your spacecraft. So 2 missions, 5 to 10 people a pop, you only need 10 to 20 people in this room, and the people actually controlling the antenna. So the computer screens that you see that are empty towards us, that's where the mission controllers would sit. But now that we have 22 missions, they wouldn't fit in here, so everybody moved out. So actually, for every single mission, there's one of these. They range in size. This is, all pretty much smaller than this. But every single mission has its own mission control room because they don't fit in here anymore. So the people that you see left are the ones that are actually in charge of the Deep Space Network itself. So they're, professionals at radio science, making sure the antennas are facing the right way at the right time, making sure the commands are being sent in the right format, the right frequency, any of the logistics of getting our message to and from our spacecraft. So that's the people you see in here. And then everybody else, it does take a lot more people than this to actually run our missions. Right? Our biggest antenna that we have is 70 meters in diameter. Now that's not the biggest antenna in the world. You've probably heard of like Arecibo or the VLA, the Very Large Array. But this is one of the largest antennas in the world that has tracking capabilities, that can actually move, right? Which is what we have to be able to do because we're having to follow our spacecraft as they're crossing the sky. So it's very difficult to build and design something like the 70-meter antenna. That thing actually rotates on a single bearing on 1/4 of an inch thick of oil. That's how this whole thing actually rotates. I think it was on National Geographic. There's a program called World's Toughest Fixes, and that was its pilot episode, fixing this thing. So I haven't gotten the chance to watch it, but I really want to. So we have one 70-meter antenna at each one of our locations, so 3 total. And then we have 36-meter antennas to talk to other things in space. The main reason that we have a 70-meter antenna still in operation is for Voyager 1 and Voyager 2. We actually had to add on to it to still be able to hear Voyager. When we talk to our spacecraft, we send a really powerful message. You know, we are screaming at our spacecraft. When they talk to us, it's like the quietest, like little whisper coming back at us. Voyager's radio, after being in space for 35 years, we are only sending a signal at about 15 watts. That's only 3 times more powerful than my walkie-talkie. Now, of course, you know, it's concentrated, so it's not an exact 3 times the power. But, I mean, imagine by the time that signal travels 11.1 billion miles, when it comes here, when it reaches Earth, that signal is a billionth of a watt strong, which is what a candle gives off. So, we have to have a giant, very sensitive 70-meter ear to actually pick up on Voyager signals. Another thing about Voyager is it doesn't have memory on board. It cannot store its data. So we are literally streaming Voyager's data from 11 billion miles away, which is pretty unbelievable. So we ask it to kind of just keep sending it. Some of its messages get absorbed into the ground. Other ones we pick up with the signal, and we kind of extrapolate from that what we can. But that's the way it works in a nutshell. Now, I already discussed a little bit about the communication delay with spacecraft and how, you know, at the time of the landing for the rover, it was 14 minutes. That communication delay is what makes it so that if we were standing in a mission control room like Curiosity's, you don't see somebody there with a joystick and a live feed of Mars. A live feed of Mars just does not exist. Any picture that we get back from space, from Mars, is, you know, let's say about 10 minutes old. And so what you're reacting to is in the past. The rover might be somewhere else at that time. So you send all these commands, then you get a new picture back, and you see the rover is at the edge of a cliff. And the commands that you just gave it will prompt it to go all the way over the cliff. But it's going to be another 10 minutes before you can actually tell it to stop. And that picture of the rover at the edge of a cliff, that's already been there for 10 minutes. Right? So it's too tricky. We cannot control our spacecraft like that. If there wasn't the time delay, we would. You'd probably see somebody like in front of an Xbox Connect commanding the rover to go places. We have that kind of technology. We simulate rovers using that kind of technology. But we can't do it because of the time delay. So we rely on the programming. So, for instance, with Curiosity, if you want to just get an idea of what it means to actually control a spacecraft, we talk to Curiosity approximately twice a day, once in the morning, once in the evening. And those times vary depending on when our orbiters are actually going to fly overhead on Mars, because we do relay messages through our orbiters on Mars. But what will happen is we send Curiosity a chunk of commands to do throughout the day. They're all timed. Curiosity has a clock on board. It knows when to do each thing. It's very smart. And then at the end of the day, before Curiosity, it doesn't necessarily shut down all night because it's not solar powered, so it doesn't have to. But before it kind of hunkers down for the evening, it will send us back everything that it learned for the day. And that's when we start working. We work while the rover is sleeping. Because what we want to do is we want to see what it did that day and then figure out what it's going to do tomorrow. And so we have a team of scientists and engineers. You'll start with the engineers reporting to the scientists with what instruments are working, what actually happened. Then the scientists say, okay, here's what I want it to do tomorrow. The scientist, you know, decides what it wants Curiosity to do, and then the engineers have to figure out what commands to actually send the rover for it to do those things. And so they work to get those commands smoothed out and ready for the next morning, and then they chuck it up to the rover whenever we have that window of opportunity. A day on Mars is 40 minutes longer than a day on Earth, which doesn't sound too bad, but it gets kind of hairy. So when we first landed on Mars, all of our engineers and scientists went on Mars time. And going on Mars time means you're subject to the rotation of Mars, even though you're here rotating on Earth. And so the shift started, Curiosity landed at about 10:40 the first night. So then the next night, our engineers and scientists came in at 11:20, and then midnight, and then 12:40, and it kept going and going and going. So they were like on permanent jet lag. And they did that for about 4 months because we didn't want to waste a single minute of operational time on Mars. And then we finally put them back on Earth time because you have to, you have to weigh the sanity of your engineers and your scientists. And we lose a day on Mars every 37 days is what it comes out to. We lose a day of operation, but that's fine. We wanted to get our Mars legs, get all of our instrument checks checked out, get everything smoothed out, all of our software ready to go so that now we can run pretty smooth on Mars. The longer our robots are in space, the smarter they get. It's not because they're smart computers, like Watson, that Jeopardy computer, or that computer that can learn chess, right? It's not getting smarter on its own. It's getting smarter because we make it that way. We upgrade its software about every 4 months or so. So Opportunity and Curiosity are 2 operational rovers on Mars now. Of the 2, when you think about their hardware, Curiosity is a much more capable rover. It can do more things. But when it comes to how it operates on the surface, Opportunity is much smarter. It's been up there for 9 years. It's like, I got this, I'll talk to you every 3 days or so. And it routes its own way around Mars. Whereas Curiosity, it comes up to a rock that's too big and it stops and it phones home and says, what do you want me to do? So we're still training it. And a lot of people think or ask, you had 7 years to build that thing and you didn't program it right? You're still working on the software. But when we land a rover, that's the only thing we train it to do, is to land. We don't even train it how to drive. I mean, we work on that software package, but then we wipe that out and we only load the landing software. So literally, when we land on Mars, we have to wipe the hard drive clean and then upload the ground software package. And so it does take time to kind of smooth things out. All right, so that's mission control in a nutshell. You have these people running the network itself. Then you have the team of people deciding what each mission is going to do. They ultimately have one ace for the mission, one person that is in charge of physically pushing that button to send those commands out. Those commands get sent to these people who send it to the right antenna, and then when the data comes back, they sift through it, send it to the engineer or the scientist it belongs to. Not all of our instruments are built at JPL. Some of them come from other places around the world. So we don't always, our scientists always at the same time have first dibs on it, but we also have to share first dibs with the people that actually built the instrument. Right? So it's very important that the data gets sent to the right people at the right time. All right, that's kind of what's going on in here. Does anybody have any questions? Yeah.
How long was it from Earth to Mars, the Curiosity?
14 minutes for the landing.